So let's discuss some boring details about implementation, about parallelization of the code, and we'll try to link it to current hardware, and you will speak a bit about future hardware as well, right?
Let's see.
Let's see. Okay, we'll see. Okay. Anyway, so. Does everybody know what an MPI rank is? Well, MPI is if you use MPI, you start these independent processes that we call MPI ranks, and that will essentially run copies of the program that communicate with each other. So explicit, there's all kinds of instructions then inside of the program to divide the work, to divide the data, and things like this. And there's explicit points where these processes hook up and exchange information. So that are the MPI ranks, these individual processes that you start. And if we look at how the work is parallelized and how the work is explicitly distributed over these MPI ranks, then at the highest level of parallelization, which is actually an optional level, we distribute over these K points that we have been speaking about. So why is this the highest level? Because it's the highest level in the sense that let's consider that we have 8 MPI ranks, and we want to divide the work over these ranks. At the highest level, we create out of these 8 MPI ranks, for instance, 2 groups of 4 ranks. Right? So in that sense, it's the highest level because it's the first division of our total number of MPI ranks. But it's an optional one. So at this highest level, for instance, if you want to distribute your work over K points, you would use this tag, set K part to something else than 1. If you set this, for instance, to 2, you create 2 subgroups of MPI ranks, and the first group would work on the first K point, for instance, and the second group on the second one, and the first one on the third, and so on and so forth. So the work on these K points gets distributed over these groups, over K par number of groups of these MPI ranks in a round-robin fashion. So this is optional, and it has been added fairly recently, and because it was sort of hacked in at a later stage, the data is not distributed. So the data structures were not set up to distribute the data over these groups. So data is replicated. So the work is distributed. The work on a particular K point gets done by a particular group, but the information, this group holds all information for all K points. And that is obviously a bit of a problematic strategy. I mean, the problem is that redesigning data structures is always much more work than doing something like this. So this is the way this was implemented, added later on. But replicating data over these groups, of course, means that your memory demands will rise. So if you have a lot of K points and you create a lot of these groups, so let's, for instance, imagine ourselves to be on a single node that has a certain portion of memory. If I now start a number of ranks on these groups and use this K par to divide the work over K points among these MPI ranks, each and every one of these ranks will allocate the full amount of memory for the wave functions. So that doesn't get distributed over K points. So your memory demands increase linearly with K par. So why is this nice to use? If you have the memory, it's nice to use this because it's such a high level of parallelization that there's hardly any communication involved. Many operations that the program does depend only on the K point itself. So it can work on this, and only at very few occasions does it need information from these other groups that work on other K points, which is very nice, obviously.
Is it better
yes?
to use this in a non-silicon system when you have the charge density already?
That doesn't matter.
Doesn't matter.
So if you have the charge density already, that would for at least for DFT, there would be really no need to communicate anymore. Because Kohn-Sham equations at a certain k point, they only couple to the corresponding equations at another k point through the density. So if you have a density and you keep it fixed, then there would be really almost no need to communicate anymore. Right.
And I have
Yeah.
a question. So when you say the data is replicated over this group, does it mean k point group 1 has to have all the rest of groups wave function saved? Or what do you mean?
It does this, yes.
Even
Though it
all
works,
the occasions just a
yes.
little bit time it needs those data.
Yes.
No, I thought what you mean is each MPI group has all the k points,
Yes.
not and wave functions both.
Oh,
Yes. So it holds the wave functions at all the k points, although it only works on a subset of them.
so yeah, okay.
Yeah. So allocation of data it isn't changed with respect to k-par, right? So even if there would be this possibility, obviously, but that would involve.
But
Yes.
wouldn't that necessarily require that for wave functions to be up to date, you need to have communication?
Actually, so they do this. They synchronize, but only at very limited instances. They do update the information of the other guys. Yes. Yes. That is true. So what does this mean? This means, for instance, that each group, so if they synchronize, so they work on the k point, on the wave functions at a certain k point, and another group works on another one, then they synchronize the wave functions. Each can use exactly the same algorithms to compute the density. They have all the informations to do this. So it's not saying that there's not another way to do this, and there's not a better way to do this, but this is the way it was. This was the quickest way to do it, and it was added as more or less as an afterthought. So why is this not the first thing that you do? This is not the first strategy that we have followed, because if you go to large systems, you will have less and less k points normally. So this is not the thing that you would. It lends itself for very efficient parallelization, but under many circumstances, it doesn't bring a lot. Because if you have a very large system, you have only one k point. Well, this you couldn't parallelize over this, right? Right. So it's not saying that this is in any way a perfect strategy, but that is the way it is, and that is the highest level. So it's the first division that we make in our MPI ranks. So the default level of parallelization is over orbitals, over these Kohn-Sham orbitals. Right. So that is within these groups. So let's assume that we have only one for the sake of simplicity. K-par is 1, so we have our original group, of the total group of MPI ranks. So the default level of parallelization is that the wave functions in their entirety, each band gets assigned to one MPI rank. And that is done in a clean way, so that there not only the work on these bands is divided between the MPI ranks, but also the data. So each MPI rank holds only the data for the wave functions it is responsible for. So that is the general the default way that VASP parallelizes, and their data is distributed as well. And okay, so that is a way you could distribute your data. Obviously, where would this run into limitations? Imagine that you have a very large cell and you put in one molecule, or maybe only an atom. You put a free atom in a very large cell. So for this atom, you would have a very limited number of wave functions that would be computed, maybe 4, right? But each of these functions would have a very large number of plane wave coefficients. Because you have a very large cell, so you have a large number of coefficients per function, but only very few functions, so you couldn't effectively parallelize then. So there's an additional level, and that's actually the lowest level where we do parallelization, and that is where we further distribute the data and the work over plane wave coefficients. So within, so now here we have our MPI ranks are assigned to work on particular bands, but we can do a further, we can combine this with a parallelization over plane wave coefficients, where I say, okay, now I can have, for instance, 2 MPI ranks that together are responsible to work on my first wave function, and then the next 2 MPI ranks are responsible to work on the second wave function, and so on and so forth, right?
Excuse me, when you create the tension, the charge density with the band parallelization, is that done in a serial way, or is it, do you see what I mean?
So these grids are divided in a different way. So
Okay.
yeah. So for densities and things like this, there's data is distributed in a different way.
But it's done fully in parallel.
Yes. Yeah. But there's communication involved, obviously.
But then, yeah, and you can't do K-point parallelization of that. is that-
Right. Yeah. So so that would be our lowest level of parallelization that and then you can make any combination of these two. And that is controlled by the tag encore. I don't know why I've written tags. Oh yeah, because there's another one that controls the same thing, but encore is the one that I would advise you to use, because I find the meaning of that tag the easiest to explain. And the other one does it exactly the same, but in a very obscure way. So if you set, normally encore is 1, which means that each band gets worked on by 1 core. So by 1 MPI rank. And if you would set this to anything else, that means that you're setting the number of MPI ranks that share the plane wave coefficients of one single one electron function. And so if I set encore to 2, my coefficients for a one electron orbital will be distributed over 2 MPI ranks. Okay, so that is sort of so that has a few consequences, and I try to illustrate it here. And it's not so important, but I would like to sort of try to elucidate what I've mentioned before. So this would be a rank, number 1 and number 2, and I have 2 of them, and encore is 1. And in that situation, my first function resides on core 1, my second one resides on MPI rank 2, and my third function resides on MPI rank 1, and so on and so forth. And if I do, and when they get worked on in terms of FFTs of these functions, that happens locally within 1 rank, right? So there are routines that, for instance, to compute these kinds of things like expectation values, like a Hamilton matrix. For instance, if I have a Hamilton matrix element between state 1 and state 4, they would need to communicate, right? Because, well, this core 1 would like to compute such an element, but it needs the information of core 4. And actually what we do is all-to-all communication. So we do a complete redistribution of the data to a situation where, so that's done internally, you don't have to care about this, but we do a complete redistribution of the data where now MPI rank 1 will hold half of each of these functions, and the second rank will hold the other half. And that makes these kind of evaluations much easier. because those are done on a plane wave by plane wave basis, so they can each now be responsible for parts of this matrix. So that is where all-to-all communication comes in VASP. So this is the other situation that I showed you, where we have more MPI ranks in this case, but we set NCore to something else than 2. So now we see that MPI rank 1 and 2 share the information of band 1 on the, and 3 and 4 of band 2, and so on and so forth. To work on those, we do parallel FFTs. So they work together to do Fourier transforms of the bands, which is necessary obviously because they share the coefficients. And to do such things, those contractions, there's all-to-all communication again that brings such a situation again in a situation where one rank has part of all the bands and the other rank has another part of all the bands, and so on and so forth. And back again if necessary. Okay, so yeah.
Since the wave functions are actually a sphere of points,
Yes.
what's your actual data layout?
Yeah, that is so. So the data layout here. So what we do, we store them. Obviously, we store only the components within the sphere.
Yeah.
For the serial FFTs, they get put onto the mesh, and then simply there's a simple 3D FFT. And here it's differently. The parallel FFT is an in-house production where you do it first along one direction. So there we do an actual sphere to cube FFT. So you do less one-dimensional FFTs than you would do it here if you would do it naively. Yeah. So yes. So some considerations with respect. So how does this? So what could you conceivably say on the outset about what would be wise choices for these parallelization parameters? Well, k-par, if you have k-points, if you have a lot of k-points or a few k-points, and you can afford the memory, then that is a very good thing to use. Always use it to its fullest. If you have large functions, if you have a lot of plane waves per one electron function, definitely use this NCore to distribute the work over MPI ranks. But do not set it to more than the number of cores, the physical cores that you have on one socket or on one package. So what does this mean? Normally, or many of the hardware, the next generation hardware is going to be slightly different, but many of the Haswell nodes, they consist of 2 sockets that have, there's a few physical cores on each socket, so let's say 10 on socket 1 and another 10 on socket 2, and those have, they have very fast access to a certain block of memory within the socket. They have probably access to the memory of the other socket, but that takes slightly more time. So for instance, for these FFTs, you wouldn't want to force the cores that reside on one socket to have to work with the memory of the other socket. That wouldn't be wise from a performance point of view. So you wouldn't set this NCore to anything larger than the number of cores per socket.
Is this specifically for hybrid version of VASP?
No. This does not pertain to the version that includes OpenMP. This is true for both actually. But the version where we use OpenMP, we don't use this anymore. I'll come to this. Yes.
So it says that NCore now works for hybrids. NPAR doesn't still, or?
NPAR and NCore are exactly the same. So, well, they're not exactly the same, but this NPAR was chosen in an idiotic way, the definition. And it's almost impossible to describe it in So NCore simply tells you I have NCore ranks that work on one function. Yeah? And the other one is sort of the inverse of it, where you say npar tells you how many bands do I do in parallel. So if I have 10 ranks and I say I do 10 bands in parallel, npar is 10, then each band gets worked on by one core.
So which version starting from? So
Sorry?
so the K-par and the N-core for hybrids from which VASP version?
It's been there for a bit, but
I know
it should definitely be in the current releases. So it's not very prominent in our manual because our manual is really sort of lagging behind by quite a bit. Yeah, which is bad. Yeah. Yes. So and you can use this level of parallelization over plane wave coefficients in connection with hybrids functionals now as well. That didn't used to be the case, but that has been resolved. Yes. So this is for our current release version, the version of VASP that is parallelized purely using MPI. The version that you have actually been working on here and that will be available to our users at NERSC is a new version that we are now beta testing that uses a combination of OpenMP and MPI, and actually, roughly speaking, the lowest level of parallelization has been replaced by OpenMP parallelization. So in that version, you can you shouldn't, if you use more than one thread, you shouldn't set ncore to anything else than one. Actually, it will simply be done by the code. Yes, so this level of parallelization will, where I would have, which you could think of as the intra-node or intra-socket level of parallelization will be taken care of by OpenMP. That has proven to be more efficient, definitely on the current hardware. Yes, so that is very nice. So, yeah, that concludes actually my part of what I wanted to say. Yeah.
Do you have any plans to do the parallelization hybrid in the GW over the four-body integrals? You know, because they're essentially to some extent independent, like some of the other codes do that now. That gives you so much more parallelization.
So we currently, for the new GW code that we have written, where we go through these greens functions, we don't parallelize over 4 electron quantities. Yeah. So I mean that would scale again like n to the power of 4, right? So because that would mean that would if we would compute our polarizabilities again using these 4 electron quantities, we wouldn't reach this cubic scaling.
If you're doing hybrids, say, then you can exploit that. I mean, other codes do exploit that level of parallelism because it's kind of orthogonal to what you want for GGA and LDA. So.
Right. No, there's no current plan to do that. No. Yes, Ling-Ji.
So you've done your lecture. I think then we can start the Q&A session a bit earlier.
Okay.
What about we use the rest of the time just to do a round table discussion, question and answer?
Okay, I thought you wanted to comment on HPC considerations as well, but
no, actually I had a running jobs, how to
okay.
VASP thing arranged for this afternoon.
Okay. Okay. So you have this for this afternoon. Okay.
think
Okay,
we
good.
can have a QA session.
Yeah, fine, sure.
So we have one online that's
Yeah.
kind of related to this immediately. Would you recommend then, particularly with the new version on Cori that has OpenMP threading, to use 1 MPI per socket?
That is not completely well for the Haswell part of Cori. I would say yes. One or two ranks should be optimal. For the upcoming Knight's Landing part, that is still a bit up in the air. What the best mix is? Yeah.
I have a question about Encore.
Yeah.
I feel like it's better to have just one, leave it at one. So where do we need to increase it? And we need more memory per band?
No. This doesn't affect your memory requirements. So both Encore equals 1 and Encore anything other than 1, that doesn't increase your storage demands. In that sense, these two levels, so these were our sort of standard levels of parallelization before this one was added. There the data is fully distributed over the MPI ranks. So that is sort of what this tries to express, right? So you can either have it reside on one band or one half on one and one half on the other. That doesn't change the amount of coefficients you have to store, right? So at the cost of communication, obviously at some point. So
So we
so
expect the speed to go up and then down. If
well,
we
there's
increase
I
it-
expect there to be an optimal point,
Yeah.
right? So if you want to go, especially if you want to go to for a largest system, if you would want to scale up to many nodes, you cannot rely on Encore as 1. You would have to increase this, definitely. Yeah.
So in the case of many K points, would it be okay to extend K par up to the number of compute nodes?
Yes, that would be in principle okay, provided you can afford the memory.
Because you multiply the amount of memory.
I mean
By
that would be sort of if you can afford it memory wise, it can be a nice way to do because the amount of communication you then most of the communication will then take place on the node and will not go through any interconnect. Yes, so that can of course help a lot, right? Yeah. The same underlying idea is mentioned here, right? So that you wouldn't increase this beyond the number of cores per socket. You wouldn't force communication between processes that do not share that are not as close to a certain portion of memory as other ones, right? So that
Could you comment on the use of OpenMP and reduction of memory? Because in Quantum Espresso, one of the uses of OpenMP is basically to deal with the large systems.
yes. So in our case, I mean, the areas where we do so in the areas where we use OpenMP as an additional level of parallelization, there's a few examples of this. Hybrid functionals are examples of this, but it's not essentially mentioned. I didn't mention that before, so I said it was a replacement for a certain MPI layer of parallelization. So in the areas where you replace MPI parallelization with OpenMP parallelization, you do not save any memory, right? Because it was distributed already. We have used OpenMP as well to introduce additional layers of parallelization, and there, of course, the nice thing is that you do, first of all, you do not have to redesign your data structure because OpenMP uses a shared memory model. and it doesn't, for the same reason, it doesn't increase the amount of memory that is used. Yes. So, but because we had already quite a lot of stuff parallelized under under MPI, right? So it is not the prime argument in that case, right? Because data was already cleanly distributed, and where it was not, we have not introduced OpenMP. So where did we not distribute the data? That was at the very highest level in this K-point parallelization. And there we don't rely on OpenMP for an additional layer of parallelization. The problem is that what we wanted to avoid is have MPI communication inside of OpenMP parallel regions. So we didn't want to, so actually we wanted to introduce OpenMP to reduce the number of MPI ranks and not increase them in the sense that I now open in a parallel region, I create 10 threads that all start to communicate through OpenMPI or through MPI. So that was sort of the idea why we have put the OpenMP parallelization at the very lowest level.
There is a magic number for the ratio of OpenMP and MPI.
If there is a magic number, and no, unfortunately not, because it would depend on system size. Because of the fact that it acts mostly at this level, parallelization over plane wave coefficients. Because of this fact, if you have a lot of one electron functions that in itself are very small, then it wouldn't bring a lot to use a lot of threads here. Neither would it bring a lot to use a lot of MPI ranks there, right? There's always if you have a lot of data, you can distribute the work over it. If you have only a small amount of data, be it bands or coefficients, the overhead will start to hurt if you distribute it over too many processes. And that, of course, depends on the particular calculation that you're doing. How many one electron functions you have, how many coefficients you have per function. Others can't be said a priori what the best mix would be. Yeah.
So one question. So OpenMP can be added incrementally in an incrementally manner. So is there any code in VASP? Like here is pure MPI, and from the end user point of view, how can we make sure we are doing the right thing?
I think the part of the code that is still almost in its entirety MPI parallelized is the part where we do linear response to magnetic fields, so the NMR part. I think for the rest, almost all, I can't think of any part that has not been parallelized using OpenMP as well. Yeah. I mean, it is still a beta version, right? So there will be still work on, and it will be still worked on, and it might change still. And it will definitely not be as stable yet as our pure MPI version. Yes.
If no more questions, maybe we stop here for the lecture.